Hello everyone, welcome to the channel Statistica. So in this lecture video, we'll go through with the topic groups, and our second topic will be rings and fields. Let's see them. So for studying groups, we first need to see what are the binary operations are. Okay, so for a binary operation on a set S, it is a map from S cross S to S. Okay, and what are our binary operations are? We have the binary operators as addition, subtraction, and multiplication. These are our binary operators on R. Okay, and you can see that the division is not our binary operator, and the question is why the division is not our binary operator. So for this, let's see that I have an ordered pair like x comma y, and it depicts that it is the image of this ordered pair is denoted by image of this is denoted by XOY, which if I'm using the addition operator, then I can write it like this, x plus y. If I'm using the multiplication one, then I can write it like x dot y. Okay, etc. For the subtraction, same. So for when I say that a division is not a binary operator, if I'm taking the operator uh, ordered set like 3 comma 0, then it means that 3 divides 0. And when 3 divides 0, but the division by 0 is not defined, by 0 is not defined. So because of this, the division is not our binary operator. Okay, so now let's see that O, we are depicting it like this, that O is associative, the binary operator O, the binary operator is associative if XOYOZ equals to XOYOZ for all XYZ belongs to S, and the binary operator is commutative if XOY equals to YOX for all X comma Y belongs to S. And in the case of composition, if we see in the terms of composition, then for any set X, composition is an associative binary operator on set of all maps from X to X. Okay. So for any set X, composition what? Composition is an associative binary operation. So that composition follows the property of associativity. Okay. For the maps from X, whenever the mapping is from X to X. Let's see it like this. I have the binary operator addition and the multiplication. These follow associativity. But negative, or we can say subtraction. Subtraction does not follow associativity, is not associative. Why? Let's see it like this. If I'm using that by associativity, I have the set 2, 3, 5, which belongs to set S. This is my X, Y, and Z. And if I'm writing it like this, 2 plus 3 plus 5 equals to 5 plus 5, which is equals to 10, and 2 plus 3 plus 5, which is also equals to 2 plus 8, which is 10. Okay, so from this we can say that associativity is following for the addition. Okay, And if I see for this multiplication part, then 2 into 3 into 5 equals to 6 into 5, which is equals to 30, and 2 into 3 into 5, which is equals to 2 into 15, which is also equals to 30. So the multiplication is also following associativity. Okay. Now let's see the subtraction part. In the subtraction part, if I'm applying 2 minus 3 minus 5, which is equals to minus 1 minus 5 minus 6, and 2 minus 3 minus 5, which is equals to 2 minus 2, which is equals to 4. So these are not equal. So associativity does not follow for negatives. Okay, this is clear from here. Now let's say the composition. Let's say I have the function f of x equals to x square, and hx equals to 2x plus 5. And we have another function, let's say 3x. Okay, if I'm using the composition f o h o u, let's find this composition first. Then f o h o u is f of h of u, and u is 3x, which is f of 6x plus 5. Okay, 6x plus 5, which is equals to, if I'm applying the function f here, then it became 6 plus 5 whole square. Okay, and if I'm using the composition f o u o h, and f, which means f of u of 2x plus 5, which is equals to f of 6x plus 15. And by this, if I'm applying the function f, it became 6x plus 15 whole square. From this, we can see that the composition FOHOU and the composition FOUOH are not equal. These are not equal. Okay. Now let's come to the next topic, which is identity element. Now we'll see the identity element in binary operators. An element E of S is said to be identity, which is depicted by I, is said to be identity for binary operator O on S if XOE equals to EOX equals to X for all X belongs to S. Okay, this is the definition for the identity element. If the composition XOE equals to EOX equals to X, then we say that it is this E is our identity element. So for the addition part, if I'm using the addition part, then our identity element is 0. For addition part, our identity element is 0. Like x plus 0 equals to 0 plus x equals to x. Okay, for all x belongs to S. And if I'm using the multiplication 1, then our identity element is 1, unity, which means x dot 1 equals to 1 dot x equals to x for all x belongs to S. Okay, and there is one point to note here, which is if an identity element exists. If identity element exists, okay, for a binary operator, then it is unique. What it is? Unique. Okay. Now let's come to the definition of group. Uh, let's come to the definition of group. What is the group? We have seen enough about binary operation. Let's see the definition of group. It says that a group is a set S together with what? Associativity associative binary operator on S such that there is an identity element and every element every element has an inverse. So from the definition you can see that there are three things to notice. When a group is a set S, a group is a set S which follows first what? Associativity with associative binary operators, okay, and second on S such that there is an identity element. Second thing is it has an identity element, okay. And the third thing to notice here is, and every element has an inverse and it possesses an what? Inverse. Like let's say x prime equals to e, which is equals to x prime x. And for x prime here is the inverse of x. What is? It is the inverse of x. And for the addition part, x prime equals to minus x, which is negative of x. And for x prime, for the multiplication part, x prime became x inverse, which is 1 by x. Okay, so this is the inverse corresponding to addition and corresponding to multiplication. Now, let's see that we are saying that a group is in a set S together with associativity binary operator on S such that there is an identity element and every element has an inverse. Okay, a group, let's say I have a group S comma O. This is our group symbol operator. That S comma O is a group if by the definition of axioms, if I'm making the axioms to this definition, then the first axiom will be x comma y belongs to S, then x o y also belongs to S. Let's see the second axiom, which is associativity, that x o y o z equals to x o y o z, which I'm saying here that associative, it has to be associative. And the third one is identity element, it possesses an identity element. So the third one is that there exists an element e of S such that xoe equals to eox equals to x for all x belongs to S. And the fourth one is it possesses an inverse. Okay, so for each element x of S, there exists an element y of S such that x of y equals to y of x equals to p, where y is the inverse of x. Okay, so this is the definition of the group. Now there is an important group which is called abelian group. Okay, in abelian group what we have is abelian group. In the abelian group, if x and y are commutative, that is if x o y equals to y o x, then we say that it is an abelian group. Okay, for all x comma y belongs to S, and it has to be commutative, then we say that the group is abelian. Okay, now let's see that if I say that S is the set for S equals to A, matrix A, and taking the matrix A with the element A, B, C, D, it is a 2 cross 2 matrix with determinant of A is not equals to 0, but and A, B, C, D belongs to R. Then we can see that the matrix multiplication AB is not equals to BA. Okay, so this is not commutative and it does not follow abelian group. It is not an abelian group. Clear? Now let's take another example. Z, which is the set of all integer with the operation of addition. if I'm taking this and taking the set like 0, 1, 2, 3, whether it will follow abelian group or not, I'm using the composition of addition. Then if I'm taking 1 plus 2 equals to 3, and 2 plus 1 is also equals to 3. So this is what? This is commutative. It follows commutativity. So it is following abelian. It is an abelian group. These are the basic examples for the abelian groups. Let's use this. Let's say that if I'm taking the set of real numbers with the composition of addition, it forms a group. This is a group where 0 is what? 0 is its identity element. Okay, identity element. And what is the inverse of this? Minus x, that is negative of x, is the inverse here. And if I'm talking about the r real with respect to the dot product, then r extracting 0 with the dot product forms a group where 1 is the identity element and 1 by x, that is x inverse, is our inverse here. Now let's say that if I'm taking r comma dot, then is it following? Is it a group or not? It is not a group. Why? Let's see this. It does not form a group. Why? See this, because it is does not form a group, because for multiplication we need an inverse 1 by x, and in the set of real numbers we have the integer 0, 2. So if this x takes the value 0, then 1 by 0 become infinity, which is not defined here. Inverse can't be infinity. Okay, so for this reason we always extract 0 from the set of real numbers whenever we use the multiplication part. Okay, so if I talk about the set of integers, the set of integers z with the composition of addition and multiplication, it forms a ring of integers. What? It forms a ring of integers. How? We'll see it. Similarly, for the complex with the compositions of addition and multiplication, and the set of rational numbers extracting the 0 part with the dot, the set of real numbers extracting the 0 part with the dot, it also forms the ring. Okay, so these are the basic group that we are forming here, and their identity element, their inverse, we have discussed them all. Now let's see the part of rings and fields. Rings and fields. In this part, let's see first the rings. What is the definition of rings? A ring is a set R together with two binary operations. And what are these two binary operations? Addition and multiplication, depicting by dot here. Okay, addition and multiplication on R, where which satisfies the following axioms. Satisfying following axioms. The first axiom here is that R comma plus, the set of real numbers with addition, is a commutative group. What? It has to be a commutative group. And the second one is that dot is associative. What? It has to be associative. And the third one is that the distributive law, which is x dot y plus z equals to x dot y plus x dot z. Okay, it can also be written as y plus z dot x equals to y dot x plus z dot x for all x, y, z belongs to R. So in the definition of group ring, we see that a ring is a set in a the set R together with two binary operations, which is addition and multiplication on R, which follows that the set on the set R with the addition, it is commutative group and it has to be associative and it follows distribution law. What is this? It is a distribution law. Okay. Now let's see the set of reals, the set of complex, the set of integers, and the set of rationals. They all form a ring. They all form a ring under the operations of addition and multiplication. The set of reals, complex, integers, and rationals. These all form a ring under the operations of addition and multiplication. Okay. Now the set of all real valued functions of a real variable forms a ring under usual addition and multiplication defined as f plus g x equals to fx plus gx for all x belongs to R, and for the multiplication part it goes fg of x equals to f of x into g of x. Okay, so this is the set of all real valued functions which forms a ring under the vector under the usual addition and multiplication. Okay, now when a ring is commutative, a ring is commutative when commutative commutative when xy equals to yx for all x and y, and the ring is said to be what? Integral domain. Integral domain. When the ring is said to be an integral domain, when it is commutative. What? When the ring is commutative. Second, it has unity. What? It has unity. Third one is if the product of any two scalars, if the product of any two scalars, two non-zero scalars actually, what? Two non-zero scalars, non-zero elements, sorry, non-zero elements is non-zero. So when a ring is said to be integral domain, when it is commutative, it has unity, and if the product of any non-zero element is non-zero. Okay. So for defining, now let's see that for defining vector space, for defining vector space, we need fields. We need fields, which is also said to be scalar field of vector space. What? Scalar field of vector space. And now what are fields? A field, we denote field here by symbol K. Okay. A field is a commutative ring, is a commutative ring such that non-zero elements form a group under multiplication. Under multiplication. Okay. So what is a field? A field is a commutative ring. It is a commutative ring such that non-zero elements form a group under multiplication. So by this definition, if I make the axioms regarding the commutative ring and the groups under multiplication, then we get the following axioms like for field, for a field, the axioms that has to be satisfied has to be, first is x plus y equals to y plus x. For all x comma y belongs to field K, it is the property of commutativity. Okay. And the second is x plus y plus z equals to x plus y plus z. For all x, y, z belongs to K, it is the property of associativity. And the third one is there is a unique element. What? There is a unique element 0 in K such that x plus 0 equals to 0 plus x equals to x for all x belongs to K. Fourth one is that to each x, there is a unique unique element minus x in K such that x plus minus K equals to 0. But this is the existence of identity element and this is the existence of inverse. Now the fifth one is that xy equals to yx. This is commutativity and xyz equals to yxyz, which is associativity for all xy belongs to K and for all xyz belongs to K. And there is a unique non-zero element. What? There is a unique non-zero element in K such that 1 dot x equals to x dot 1 equals to x for all x belongs to K. What is this? Is the existence of identity, and to each non-zero, the eighth one is to each non-zero x in K, there corresponds an x inverse of 1 by x such that x inverse equals to x inverse x equals to 1. Okay, and the let's write here. And the ninth one is the distribution one, which is x of y plus z equals to xy plus xz. So what we done here is we have just combined the properties with respect to the addition and with respect to the multiplication, which we have used in the rings. This is the definition of the ring, that a ring with respect to the addition is commutative and with respect to the multiplication it has to be associative and it follows the distributive law. This is what it is, what distributive. Okay, so what are the fields here is that a field K is a common ring such that non-zero elements for a group under multiplication. The first four axioms which is commutative with respect to the are with respect to the addition, which is commutative, associative, existence of identity element, and existence of inverse. These four axioms are with respect to the addition one, and the last four axioms, which is um, commutative, associative, existence of identity, existence of inverse, are with respect to the dot, which is multiplication one, and the last one is the distributive law. Okay, so these are the 9 axioms which has to be satisfied for any set to be a field. Okay, let's see that the set of real numbers are plus dot. What it is a field, the set of complex with the operations of addition and multiplication, it also forms a field. Similarly, the set of rationals, it is also a field, and the set of integers. If I'm talking about the set of integers, then it is not a field. Why? We'll see that. The set of integers is not a field because in the axioms we can see that the set of integers will satisfy this property of commutativity, associativity, identity, and inverse. This one too, but it doesn't satisfy the else property, which is the each non-zero x in K, there has to be an inverse x inverse. So because the set of integers does not contain the element like 1 by x. It does not satisfy the property of x because it does not possess an inverse. So the set of integers does not form a field. Okay. So this is all about the fields, rings. Now let's meet in the next lecture. Thank you.